Hello students, welcome to EPG Parshala. I am Sumalay Roy from Department of Physics and Astrophysics of University of Delhi. Today we are going to discuss about the module Heisenberg's uncertainty principle. This is from the paper Quantum Mechanics. In this module, we introduce the concepts such as Heisenberg uncertainty principle and the complementary principle enunciated by Bohr. While constructing the wave packets in space and time, we noticed that there are fundamental limitations placed by the wave packet representing the particle on the accuracy with which both the position and the momentum of a particle can be specified. We found that if we construct a wave packet in space which has a spread delta x, then the range of width delta k, where k is the wave number of harmonic waves superposed. This delta k is related with delta k greater than or equal to 1 upon delta x. In fact, this is a result quite generally known from the theory of Fourier transform. In other words, the spread in momentum delta p of the de Broglie waves contributing to the wave packet satisfies an inequality which is delta p into delta x is greater than equal to h bar. Similar inequality between energy and time also holds when you consider a wave packet in time constructed from the superposition of a spectrum of harmonic waves in frequencies or angular frequencies. This is the essential content of the uncertainty principle, which we shall be studying in this present module. The underlying idea that the physical variables describing the basic properties of matter, such as momentum and position, do not exist in a precisely defined form in quantum theory constitute a far-reaching change that led Bohr to enunciate it in terms of what we call the complementary principle. This will be illustrated through the example of a double slit experiment in the present module. Determination of position when momentum is precisely known, the gamma ray microscope experiment. Let us illustrate the uncertainty principle through a measurement experiment, which was first discussed by Heisenberg to measure the position of a particle as accurately as possible. The basic idea is to show how quantum effects intervene to prevent measurements of unlimited precision. Suppose we wish to determine the position of a small object with precision using a microscope. The limit to the accuracy delta x with which a position determination can be made is given by its resolving power, which is delta x equals to lambda by sine alpha. Here lambda is the wavelength of the radiation that enters the objective lens, and alpha is the half the angle subtended at the position of the particle P by the objective lens, as shown in the figure 5.1. This would decrease the resolving power of the lens due to increased diffraction effects. As a result, there would be a proportional decrease in the accuracy of the position measurement. Thus, no matter how we perform the experiment, a limit on the accuracy of the measurements corresponding to the uncertainty principle would always be introduced at some point in the experiment. Momentum determination experiment. In the above experiment, it is assumed that the momentum of the particle is precisely known before the measurement is performed. We found that the measurement not only gives an inaccurate position determination, but at the same time introduces the uncertainty into the momentum. Let us now consider a different experiment in which the position is accurately known initially and the momentum is measured. Complementarity principle, the double slit experiment. Let us revisit Young's double slit experiment showing the interference of light, or equivalently of a beam of electrons instead of light. In the context of uncertainty principle here, and let us probe the question, can we say that the photon or electron which reaches some point of the interference pattern has followed a definite trajectory passing through a particle one of the two slits? The probability interpretation, which was earlier introduced, makes it abundantly clear that we cannot. Let us assume that the particle has a trajectory. Because of the wave nature of the particle, a sharp trajectory is not possible. Let us suppose that the trajectory is a moving wave packet with lateral extension less than half the separation A between the two slits. This assumption is made to ensure that it can go through only one of the two slits. Can there be an interference pattern then? Let us try to answer this question from the point of view of uncertainty principle. Having studied this module, we have come to know the statement of Heisenberg uncertainty principle. We have come to learn through a measurement experiment how the process of trying to determine position precisely using a precise value of momentum. This not only gives an inaccurate position determination, but at the same time introduces the uncertainty into the momentum. We have learned through another measurement experiment that even if the position is known precisely, the process of measuring momentum not only gives uncertainty in the momentum measurement, but at the same time introduces uncertainty in its position. We know through a few typical examples the implications or the consequence of using the uncertainty principle. We have learned the complementary principle given by Bohr. Thank you.